This video looks at conjugates of complex numbers, also known as z bar. Now, the conjugate of z equals a plus bi is simply z bar equals a minus bi. So we just swap the sign that's in the middle. And you'll note that when we multiply a complex number by its conjugate, so a plus bi times a minus bi, expanding just like we would algebra, a times a is a squared, a times negative bi is minus abi, bi times a is plus abi, and bi times negative bi squared would be negative b squared I squared. You'll note that these terms in the middle cancel each other out, so we're left with a squared minus b squared I squared, but I squared equals -1. So therefore we have a squared minus b squared times -1, which is a squared plus b squared. So we're left with a real number. Now I kind of relate this to rationalizing the denominator. When we rationalize the denominator with our surds, we times by the conjugate, which gives us a rational denominator. So to me, this is very similar to doing that. Now, the modulus of a complex number z equals a plus bi is denoted by the absolute value. Now, that's no different to what it was in vectors, being the size. Okay, so the absolute value of z is the square root of a squared plus b squared, which, as we just found out, a squared plus b squared is our complex number times by the conjugate. Okay, so that means that the complex number times the conjugate has to be the modulus squared. Now, just as a side note, and this will make more sense when we do get to graphing, which we're not there yet, but when you do get to graphing, we talk about the imaginary plane and the real plane. So if I've got a plus bi, let's just say this is a plus bi here, then this distance here is a, and this distance here is b, isn't it? Because this would be my a, and this would be my b. So that there is our modulus, which of course, using Pythagoras, is the square root of a squared plus b squared. So you can see where that's coming from, and this will make more sense when we do get to graphing. So you should see the relationship to vectors. It's just we're talking about a real axis and an imaginary axis, our real numbers versus our imaginary numbers, or our real parts versus our imaginary parts. So let's look at an example. If Z1 is 5 minus 2i and Z2 is -1 plus 3i, find the conjugate of Z1 plus Z2. So Z1 plus Z2 would be 5 minus 2i plus -1 plus 3i. 5 minus 1 is 4, -2i plus 3i is plus I. So the conjugate of that would be 4 minus I. In contrast, it wants us to do the conjugate of Z1 plus a conjugate of Z2. So the conjugate of Z1 would be 5 plus 2i. The conjugate of Z2 would be -1 minus 3i. So the conjugate of Z1 plus the conjugate of Z2 would be 5 plus 2i. Take 1 minus 3i. 5 minus 1 is 4. 2i take 3i is minus I. And you'll note that they are the same. Next one, the conjugate of Z1 times Z2. So firstly, Z1 times Z2 would be 5 minus 2i, -1 plus 3i. That's -5 plus 15i plus 2i minus 6i squared, which is negative 5. 15 plus 2 is plus 17i. My I squared is equal to negative 1, so that's plus 6. Negative 5 plus 6 is 1 plus 17i. So the conjugate of that would be 1 take 17i. Now let's look at the conjugates times by each other. Now we have the conjugates in part A. So Z1 was 5 plus 2i, the conjugate of Z1, times by the conjugate of Z2 is a negative 1 minus 3i. So that's negative 5 take 15i minus 2i minus 6i squared. Negative 5, negative 15 take 2i is negative 17i. Remembering that our I squared is negative 1. So that's plus 6. Negative 5 plus 6 is 1 take 17i. So you'll note again that they are the same. Okay, so then I've just summarised that at the bottom. The conjugate of a sum is equal to the sum of the conjugates, and the conjugate of a product is equal to the product of the conjugates.